Alright gang, I'm adding another little video here on section 14.1. It's just on the independent assortment idea that happens at the very end of section 14.1. I don't think this is a very difficult concept, but I want to go over it, highlight it just to make sure that you understand the passing on of different alleles to offspring, especially if you're looking at more than one trait at a time. That's when things can get just a little bit confusing. Anyway, the law of independent assortment basically came down as a question when Mendel started to look at different traits at the same time, multiple traits at the same time. And so, for example there, if we look at this cross that I'm showing right here, this is again from a diagram in the book, if we look at this P versus this P, there's two traits that are noticeably different between them. One is the color, yellow versus green. The other one is that this is round and this is all wrinkled. Okay, and these are two different traits that he studied, and he found when he was just looking at the color, he found that yellow was dominant to green. So again, when we do our symbols with the yellow and the green, typically we'll use for the dominant, we will use the capital letter that is the first letter of whatever that trait is or that character is. So if we look at yellow, we're going to use a capital Y. So I have that written over here, capital Y. And then the recessive, we're going to use the same letter because that indicates that it's the same type of gene, but we will use the lowercase, so the capital Y. Lowercase y. If we used a different letter, like sometimes people are like, why don't you use a lowercase g for green instead of y? That would be because if you used a capital Y and a lowercase g, then people who study heredity, geneticists, anyway, they would take that to mean that they are different types of genes, when in fact they're the same type of gene. It's the color gene, and there's two versions, the yellow and the green. So we use the same letter because it's the same type of gene. When we look at round and wrinkled, they found out that round is dominant to wrinkled when he was doing the independent crosses, just looking at the shape of the piece. So anyway, when he did this cross, the big question was, if he starts to look at two different traits at one time, will they work independently of each other? Meaning, when we go through the results, are we going to find that this is yellow and round? Are we going to find that the yellow and the round behave independent of each other? Or are we going to find out as we go through the generations that the yellow and the round end up always staying together, meaning that they're connected to each other? Okay, same thing over here. Are the little y and the little r? Okay, are they connected to each other, or do they work independent of each other? Okay, he did a cross between these, and what you would expect there actually happened, where the first set of offspring were all yellow and round. Okay, and the reason you would expect that is because if I look at this parent, this first parent up here, it can only pass, it's pure yellow, pure round, it can only pass to its parent yellowness and roundness, and both of those are dominant, so those are going to have to show up in the next generation. They have to. Okay, these recessive genes have to disappear in the next generation because they're recessive. Okay, the big question here, and actually just some notes, this is actually the reason that I wanted to show this. Notice that this parent is passing on a Y and an R in this gamete. These are supposed to be the gametes here. They're both there, and a lot of times I will have students that they'll say, hey, this could either give a capital Y or it could give a capital R to its offspring, but they have to give one letter for each trait. Same thing over here, it has to give at least one Y and one R, and no more, no less than one Y and one R. Okay, so then we get this offspring. All of them got a capital Y and a capital R from this parent. All of them got a lowercase y and a lowercase r. Anyway, these are called dihybrids. These this first generation here, they're called dihybrids. The reason they're called dihybrids is because they are a hybrid, which means mixture, for two traits. This is a hybrid for the YY, the capital Y lowercase y is a hybrid, capital R lowercase r is a hybrid, and so this is a hybrid for two different traits, therefore it's a dihybrid. So the next step for Mendel would have been, let's do a dihybrid cross, meaning let's cross a dihybrid with another dihybrid. So I'll just write this in here really quickly, change my pen color to black actually. So we have our first dihybrid is going to be crossed with another dihybrid, capital Y, lowercase y, capital R, lowercase y. Hey, real quick, just on a little note, I have lots of students in general biology class that when they take these gametes up here, and decide to combine them, they combine them and they write it this way: capital Y, capital R, lowercase y, lowercase r, and they kind of keep what was in the gametes, they keep them separate from each other. And that's not right. Notice the correct way to do it is to take the y's from this and from each of the gametes, take those two y's and put them together for a big Y, little y. Take the two r's, put them, it's just the proper format, it's the way that, that people do it. So, let me get rid of that. So now if we go to the next generation, what we have to do is figure out, and this is the part that I wanted you guys to see, figure out these dihybrids, okay? What are the possible gametes that this dihybrid could produce, okay? Now we've got two options. If the capital Y and the capital R, if they happen to be connected to each other, meaning wherever the capital Y goes, then the capital R goes with it. Okay, that would be if they're connected. If that were the case, then when we go to come up with the gametes from this individual, we would get the following. They could pass on gametes that have the capital Y and the capital R, okay, or they could give on gametes that have the lowercase r and the lowercase y, okay. That would be it. That's one possible gamete. There's the other possible gamete. That's if they're connected. Okay, and that would apply to both parents. Remember, this is a dihybrid cross. So if that were the case, that's the way it would be. If we kind of look at the results down here, what they found, if I slide this down, if I follow to the left here, sorry, having trouble with my pen. If I follow to the left here, this is saying what would happen if they're connected, meaning each parent, so I'm doing a Punnett Square, each parent could give a big Y, big R, or a little y, little r. Okay, and those are the only options. What we would see is in our results, when we fill in this Punnett Square, we would see that we would expect to see 3 yellows for every 1 green. Okay, and when Mendel did his crosses, it did not turn out that way. It ended up being these numbers on the bottom here is what he ended up seeing, which do not follow a 3-to-1. It doesn't follow 3 round and smooth with 1 wrinkled and green. It's not that ratio at all. In fact, we're seeing phenotypes that don't even exist in this Punnett Square. Okay, we're seeing the phenotype green and round. It's not even in here. Okay, so that meant, that's why there's this big circle, whatever, in here. That means that it could not be that these, the Y's and the R's are linked together. Okay, which means they must work independent of each other. Okay, and this is where the law of independent assortment comes in. It means that however the Y's are passed on, that's completely independent of however the R's are passed on. Okay, so what we have to do is we have to go through again, if we're going to figure out the probabilities of the offspring, we have to go through and figure out what are the possible gametes that this dihybrid could produce if the Y's and the R's are not linked to each other, if they're working independently. So the way that you would work this is I would look at this and I'd say, hey, one possibility of Y and R combination, I could have a capital Y with a capital R. That could happen. That could be the matchup. Or I could get a capital Y matching up with a lowercase r. Okay? Or I could get a lowercase y with a capital R, or a lowercase y with a lowercase r. Okay? That's all the possible combinations of these y's and r's that you could find. Okay? So our Punnett Square reflects that. There's 4 possible combinations. So from one parent, we have our 4 possible gametes lined up on the top. The other parent with the 4 possible gametes lined up down the side. And when we fill in the Punnett Square, bring everything in together, blah, 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 we end up seeing 4 different phenotypes, 4 different phenotypes. And our ratios work this way. Our yellows that are also round, that's one of our phenotypes, there would be 9 of them in this Punnett Square. Okay? The yellows that are wrinkled, there happens to be 3 of those. The greens that are round, there's 3 of those, and there's 1 is both recessive alleles, okay, or both recessive traits showing up, the green and the wrinkled, okay. 9 to 3 to 3 to 1 would be our expected ratio, 9 to 3 to 3 to 1. Well, when Mendel did his crosses, this is what he found, that there was roughly a 9 to 3 to 3 to 1 ratio, okay, which supports this Punnett Square and the idea that independent assortment happens, meaning the different genes are not attached to each other in any way. They work independently of each other. So that's independent assortment. Honestly, the reason I wanted to show this is because you're going to be doing some two trait crosses in the near future, and I think it's it's important for you to see how we come up with the different types of gametes from this parent, the different gametes from this parent and this parent, and then how we set up the Punnett Square. So I think that's it for this video. Actually, my intention here is when I'm done with this one, I'm going to put a couple videos on with some simple Mendelian genetics problems, where it says, like, if I cross one thing with another thing, what would their offspring look like? So I'm going to put a handful of those onto on a video and just kind of show how I would work through those problems, or what the logic is with those problems, and then we can move on to section 14.2, which gets into some probability, which is good. So that's it, and we'll see you in class.